Hi, so welcome back. So in this lecture, we will learn about the Cauchy-Euler form of solving a second order linear differential equation. So this is the first type of second order linear differential equation where we have non-constant coefficients for these differentiated terms. Okay, so before this, all the coefficients of x double prime and x prime and x, they were all constant terms. For example, before this we had just 1 and we had a b over here next to x prime and just a c next to x. But now we look at a differential equation of a very specific form where the constants or the coefficients take up specific because the coefficients look very specific. The coefficient that goes with x double prime is the t square term. The coefficient that goes with x prime is t, but of course multiplied with the b before. So we keep the b as it was before, and for this one it remains as it was, c, and c is the only coefficient for x. Okay, so this is a very specific differential equation. It's a form of a differential equation where instead of constant coefficients like before, we have very specific non-constant coefficient terms for these differentiated variables here. Okay, now this is worth solving because this is an important form. It comes up a lot of times when you're trying to solve Laplace's equation, for example, in cylindrical coordinates. Of course, we're not going to go deep into that, but it's an important form because various differential equations in various fields may actually, maybe after a bit of a substitution or transformation of variables, can give rise to a differential equation which looks like this, okay? And so to know how to solve this differential equation would actually help solving all those differential equation problems. So it's an important form in that sense. So let's just see how to solve it. So first we want to find out what would be the complementary function. In other words, the homogeneous solutions of this differential equation. So when we want to find the homogeneous solutions, we want to make the input term on the right 0. Okay, so first we're looking at homogeneous solutions. Okay, for that we want to rewrite this differential equation t square x double prime plus b t x prime plus cx, but with a 0 the 0 term, a null term, okay, on the right hand side as 0 external force or 0 input to the system. Okay, so to solve this differential equation, the reason I've written this to find the homogeneous solutions of this differential equation, we want to try a different kind of a trial solution. Okay, it's going to be t to the m, okay, for a differential equation in the Cauchy-Euler form. Okay, previously the trial solutions that we always tried were of the exponential form e to the mt. Okay, so they were of the form before the trial solutions were of this form, x was e to the mt. Okay, but that doesn't work for a differential equation of this form with these non-constant coefficients. Perhaps we can see why. Okay, so let's just see why this won't work for if I want to find a solution for this differential equation. Let's take in x equals e to the mt here and see why this doesn't work. Okay, so if I want to do that, I have the t square. So I'm trying this now. So I have the t square term as it is. X double prime is the double differentiation, so it brings in the m square term, keeps the e to the mt term as it is. I'm not writing it here because that will be e to the mt will be common to all the terms, which we can finally take out and then eliminate because we have 0 on the right hand side. Then we have b, this t remains, and x prime brings m down once, keeps e to the mt, which we're not writing. Then we have the c, and of course x would be e to the mt, so that we're not writing. Okay. Okay, so what you have is, so this gives me So this is 0, okay, if I eliminate e to the mt term, as it's very evident because it's common to all the terms, and there is a 0 on the right hand side. E to the mt is never 0, so you can eliminate that. So this is what you're left with. So you have to find this m, remember? Okay, so now this is a second. So what this is if you look at it, this is Tm squared. This is Tm. So this is a quadratic equation in this variable Tm or Mt as this index here. Okay, this index here, you get a quadratic equation in that index. Of course, if you solve it, if you solve for this variable mt, you get some constant. Okay, if you solve it, you're going to get minus b plus minus root over b square minus 4c over 2. Okay, that's a constant. That's a constant term because all of these are constants. B, c, and everything are constant. Okay, so really, what this is telling us, if you stick in e to the mt as a trial solution here, the answer you get is e to the, well, mt is a constant, some constant a. Okay, so the trial solution for this differential equation is a constant solution, which is absurd because we don't want constant solutions. Of course, if this is a constant solution for this, if I stick in e to the a here, double differentiation makes it 0. If I stick in e to the a here, one-time differentiation also makes it 0. If I stick it this here, of course it's not 0, but that means that c must be 0. Okay, so, and in order to get a 0 on the right hand side, so what we get is a constant homogeneous solution, which is something that we don't want. Okay, we are looking for non-constant solutions. Okay, so this really doesn't work. Okay, so we are not going to try that therefore. Okay, so what works instead is t to the m, and you can definitely see why once we stick this in. Okay, so let's try t to the m here. What happens to if I try this? So let's just rub this out. This is out of the question. Okay, so let's try t to the m over here. So you get t square as it is. Double differentiation of this t to the m gives me m and an m minus 1 and a t to the m minus 2, okay, plus b, this t, and a one-time differentiation is m t to the m minus 1 plus c, of course t to the m is equal to 0. Now you can rearrange this a little bit. This t square multiplies with t to the m minus 2 to give you the t to the m term. So you have m minus 1, you have t to the m term, plus b. This t again multiplies this one to give you a t to the m term. So you have bm t to the m, plus of course you have the t to the m term from here. Of course t is the independent variable. Okay, we don't want t to be 0. Okay, otherwise the differentiation makes no point. So if t is not 0, t to the m is not 0. So you can eliminate t to the m from the left hand side because you have a 0 on the right hand side. So really what you get is m. So if I write this down, if I eliminate the t's from here, let me just rub this out. So this is what you get. If you rearrange this a little bit, what you get is m squared plus b minus 1m. There's a bm from here, and there's a minus m from there, okay, plus c equals 0, okay. And now this makes sense because if you want, so let's say m gets two roots, m1 and m2, okay. If these are two roots, of course, they can be equal as well, as we have seen before. And those were the different cases, the cases for, critical damping or resonance. But let's say that m gets these two variables or these two solutions from here, m1 and m2. Then, of course, the two homogeneous solutions, these were the trial homogeneous solutions. So the two homogeneous solutions would be, let's say, the first solution is t to the m1, and the second solution will be t to the m2. And of course, therefore, the complementary function, as before, will be a linear combination of these two homogeneous solutions. So it will be something like C1, the first solution, which is t to the m1 plus C2 t to the m2. That would be the complementary function. Okay. So therefore, this worked. Okay, this trial solution worked. Why it worked is because of this critical step here. Once we are differentiating t twice, you're getting a t to the m minus 2, and you already have the t squared term, so that gives the t to the m term here. Remember, t to the m differentiated 1 gave me the t to the m minus 1, but you already had the t here, so that made that t to the m, and of course the t to the m from here. So the t to the m term comes out common with this trial solution, which you can eliminate, and now you have a valid auxiliary equation. This is the auxiliary equation to solve, from which you can get two solutions, which would give you the two homogeneous solutions, and then combine them together in a linear form, and you will have the homogeneous solution, the complementary function. Okay, this is the complementary function. So if you want, I can. So this is the complementary function. Okay, the complementary function, right? So of course, a slight. Yeah, I mean, so let's just come back to this trial solution here. Okay, so how is this different from the previous trial solution? Okay, let me just write it. So the trial solution that we are using now is t to the m. Okay, but how is this different from the previous trial solution, which was an exponential form of this type? Okay, m to the something. But can I connect the two? The way we can connect the two is if I write the logarithm of t here. This is the natural logarithm, but I'm writing it as log. Okay. If e to the m times log t gives you t to the m. Okay. So really, what you tried as a trial solution, we tried the trial solution of this form itself. Okay, exponential form, which we have tried all along this course, okay? Except that, but before we tried solutions where the variable here was t. But now, the variable that works for this differential equation is not t, is log t. The natural logarithm, okay? So really, the form of the trial solution remains the exponential form, but now with a different variable. And once you, instead of t like before, once you stick in log t, then you get t to the m, which actually works for this. So the only difference between solving this Cauchy-Euler form of second order linear differential equation and the previous forms that we have solved with constant coefficients is that the trial solution, so let's just write it here. For this one, the trial solution is e to the m logarithm of t, which actually is t to the n. Okay, so that's the only adjustment that you have to make to the trial solution to get a valid complementary function for this differential equation. Okay, all right. So now, of course, we can give this some name. Okay, let's call the z or z. So in other words, so remember t was the independent variable, and we are naming log t as something else. So we are introducing a new variable. Okay, in other words, we are sort of substituting for t. We're substituting a new variable for t. And if you write z instead of log t, then the trial solution becomes the previous form. Okay, in this new variable, instead of t, if you write log t as z, in this new variable z, the trial solution remains the kind of trial solution that we have seen all this while. Okay, so the trial solution remains the same or the same form that we are used to if you substitute for log t z. Okay, and in this substitution, with this substitution, this works out. Okay, what happens in this substitution? What happens to, how would this change? How would this differential equation, the form of the differential equation, change if you substitute z for log t? Okay, remember this, there is a t here, there is a t here because it's a differentiation of x with respect to t. So all these are dependent on t. They're all functions of t. So once you change, once you write z for log t, this entire left-hand side form will change. Of course, also the right-hand side. Okay, because t really is e to the z. Okay, if z is log t, t is e to the z, so this will become f e to the z, and now this becomes a function of z. And once you substitute for log t z in the left hand side, this also changes its form and it becomes a function of z. Okay, right. So what will that form be? Well, thinking about t to the m as e to the mz, where z is log t. Okay, if I change this, then this is e to the mz. Okay, the way this is going to change is, so everything remains the same. Let's see what this becomes. Okay, it's just, we have just renamed some variables. Okay, we have just called log t as z. Okay, so everything else remains the same. If I want to see, this was the complementary function. This is actually t to the m. They're the same. Okay, but this is the complementary function of this homogeneous form. Okay, in terms of this new variable, if I look at x now as a function of z, because t can be expressed as a function of z, if I want to see x as a function of z, how will this look? This will look like c1 t to the m1 will be e to the m1z, okay, plus c2 e to the m2z, right? The complementary function in terms of t looked like this, but in terms of z, just by using this t as e to the z or z as log t, x as a function of z will now become this. Okay, that's the complementary. This is the complementary function in t. This is the complementary function in z. So it's a complementary function in z where these two roots, or m1 and m2, are roots of this differential or this quadratic equation. Okay, so if these are the roots of this quadratic equation, what would be, let me rub all of this out, you know this now. So come back to the question. If this is the complementary function with m1 and m2 as roots of this quadratic equation, then what would be the differential equation? Whose complementary function would this be? It would be d2x dz2 plus b minus 1 dx dz plus cx equals 0. This is a second order linear differential equation with constant coefficients. Remember, there's a 1 here, there's b minus 1 and there's c, whose auxiliary equation is this. See? Remember how auxiliary equations came from differential equations? You just replaced the second order term by m square, the first order term by m. So this is the auxiliary equation of this differential equation. And m1, m2 are the two roots, and this is the complementary function. So if we had a differential equation like before, where we had only constant coefficients like these, then this suggests, because this complementary function is of the form that we have known, this suggests that this must be the ordinary differential, second order linear ordinary differential equation, whose complementary function, or whose solution actually, because there is 0 on this side, will be this. Okay, and it will come through this. Okay, this would be the auxiliary equation. The two roots would be this, and that would give me this. Okay, now and why would I have z here? Because remember, for a differential equation with t as the independent coefficient, we had t over here, but now because we have z here, this suggests that the independent variable in the differential equation must be z. Okay, so transforming this t to z, in other words, writing log t as z, the way it transforms the left hand side is it makes it this. Okay, see, we are dealing with homogeneous solutions. Okay, so we're not concerned about the right hand side. We're only dealing with the left hand side. That's the form which will change if we substitute this. Of course, the right hand side changes to just this. There's nothing more to it. Okay, but the left hand side changes in its form, and this complementary function, because I can write this complementary function in terms of z as this suggests that the way the left hand side should change should become this particular form. Because solving this to get this is the homogeneous form of this equation. We solve this to get this, but this is the same as this, and this is the solution of this. So these two must be the same. Does that make sense? We solve this homogeneous. Well, we'll do that one more time. We solve this differential equation, a homogeneous differential equation with 0 on the right, to get this as a complementary function. But of course, with this substitution, I can write this as this. And this we find will be the solution of this differential equation. And they're equal. So therefore, the root differential equations, or the mother equation, differential equation, must be the same. So the left hand side, this must be the same as this. So the way this transformation z equals log t changes the left hand side is that it makes the t square x double prime btx prime cx, it makes it the double differentiation of x with respect to z. It makes it a second order differential equation with constant coefficients. In other words, it gets rid of the t squared t and all these terms, and it gives you a second order linear differential equation with constant coefficients, things that we have already solved. Okay, so that's the beauty of this. Okay, that's how it all connects. That if you try this solution, the way you're going to transform this differential equation with this substitution is going to be this. So in other words, let's just write everything down. So if you're going to solve this differential equation, it's a summary of all the reasons and the logics that we have just gone over. If you substitute z equals log t, okay, what you're going to get with this substitution, the left hand side will become a double differentiation of x with respect to z plus b minus 1, this changes to b minus 1 from, and it was evident from the auxiliary equation, and this becomes dx dz plus c x. Okay, remember here we are viewing x as a function of z. This x is a function of z, x here is a function of z. And the right hand side just becomes f of e to the z. Okay, with this substitution. And really, now you can solve this. Okay. And we have already seen the complementary function. Let's write c for here. For complementary function will be c1 e to the m1 z plus c times e to the m2z, and of course m1 and m2 are roots of m square plus b minus 1. Now with this substitution we are solving this. m1 and m2 are roots of this. This is what it should be if of course m1 and m2 are not equal. Okay, and of course in terms of t, this should be c1 t to the m1 plus c2 t to the m2. Okay, and this is when m1 and m2 are not equal. Okay, right. Now if m1 and m2 are equal, then what happens? Then what's the complementary solution? Complementary function. m1 and m2 are equal, then the complementary function becomes c1 e to the m1 z plus c2 z e to the m1 z, right? This is what happens when m1 and m2 are equal. In other words, that's the case of resonance, that's the case of critical damping. Okay, or this middle term 0. Okay, that is b is equal to 1. If b is equal to 1, that's the case when m1 and m2 are the same. Okay, sorry, not b is equal to 1. The case where b minus 1 square is equal to 4c. Okay, that's the case of critical damping. What happens here is, if you substitute this, you get c1, of course this is t to the m1 plus c2, this is t to the m2, but z here is log t. So you're going to get a log t term. So if the complementary function, if in this differential equation, if this is what it is, if b minus 1 whole square is equal to 4c, in other words, the transformed differential equation had the two roots of the auxiliary equation the same, then the complementary function would be, in terms of t, that's the variable in which we have to solve this differential equation, because it's given in t, it's going to be this. And if the two are complex numbers, for example, alpha plus I beta, okay, that's the case when b minus 1 whole square is less than 0. Okay, this is the case when b minus 1 whole square is equal to 4c. This is the case when b minus 1 whole square is less than 4c. Okay. This is the case of no damping. Okay. And this is the case of overdamping when b minus 1 square is greater than 4c. Okay. What happens here is, remember what the solution was before. The solution was when you had these complex terms, it was you had e to the alpha z, okay, e to the alpha z, some constant c1 cosine beta z plus some constant c2 sine beta z, if this was the solution of, these were the two solutions or complex solutions of this auxiliary equation, then the complementary function of this would be this. But of course, in terms of t, that would be, let's just write log t here, okay? That would give us t to the alpha, okay? You would get alpha log t would be log of t to the alpha, and exponential raised to that would be t to the alpha. Then you have c1 cosine beta log t plus c2 sine beta the log of t. Right. So really, the way we can solve, and we have all the forms now, okay, just by looking at this transformation, how we can transform this given, this new form of this differential equation with non-constant coefficients, we can transform this back to a form which we are already familiar with, and we know all the forms of the homogeneous solutions, or all the forms of the complementary function. And by this simple substitution, we can just write down what would be the exact forms, okay? What would be the forms of the complementary function in these various terms, the case of no damping, over damping, and critical damping, okay? Right, so that gives us a very clear picture of what it is, okay? How to solve this differential equation, at least the homogeneous form, the complementary function of it. Once you do that, the right-hand side, bringing the right-hand side in other words, bringing the particular solution, trying to find the particular solution of this, is just the same as finding like what we have already done before, okay? So for example, if the right-hand side, if this right-hand side was, let's say if this was log of t, then the way the right-hand side would change would that this would become z, which is a polynomial input, okay, of degree 1, and we know how to solve that. We will get a particular solution, okay? We will get a particular solution in terms of this, okay? Let's just solve this, okay? Let's just solve this, okay? With z over here, okay? What would the particular solution of this be? It's very easy, okay? I'm going to rub this out. We know the homogeneous part. Let's just write, what if I have a log t over here? That makes this, okay, so this is really solving the particular solution in terms of z here, remember, okay? And this is given by 1 over d squared plus b minus 1 d plus c on z, okay? That's the particular solution. Remember, in the operation, in the d operator form, okay, this is how the particular solution of z would look like. And of course, we already had a form for this, okay? The form was really, and we worked this out in the first assignment, and also while doing the d operator with polynomial inputs on the right, we already had a formula for this. The formula was, if you had a polynomial on the right, if you had p on the right, the particular solution was equal to 1 by c times p minus b over c square dp dt plus b minus c square over c cube d2p dt2. This was a form that we had already done using d operator method, using our knowledge from the first assignment, okay? And we can just use that formula here, okay? So the particular solution is just, this is the p is z here, okay? So that's, therefore, using this formula is just going to be 1 over c is what it is, okay? P is z minus, well, b in this case is b minus 1 because this b was when we had a b here, okay? So this is b minus 1 over c square, okay? And dp we're doing this with respect to z now, so you can think of, so this will become minus 1, and this, all of the independent variables will change to z, okay? And this is, of course, b minus 1 now, okay? So b minus 1 over c squared, dp dz is 1, okay? Because that's dz by dz. And a double differentiation of z with respect to z will be 0, so there is no other term. So the particular solution is just this, okay? And therefore, the particular solution, if you stick this in back, okay, you're going to get 1 over c log t minus b minus 1 over c squared, okay? That's your particular solution, okay? Now, this is, of course, viewing this as a function of t, okay? This was the form when you thought of this as a function of z, okay? All right, so that's the particular solution. So the way you solve this is, and that's the entire thing. You just put all of them together. The entire solution will be whatever the complementary function comes out to be, plus you put that together with the particular solution, okay? This particular solution, and that's your general solution, okay? So this is how you solve Cauchy-Euler form. There is a more technical method of showing that this left-hand side turns into this left-hand side, okay, with this substitution, by doing a bit of a differentiation, okay? If you differentiate dz, if you change the independent variable in terms of this, okay, by doing a bit of a differentiation here, you can get this. You can also show that this comes to this, which we can put in the assignment perhaps, but at least from logic, at least from the way things pan out, we can see that this change is very obvious from the way the complementary, the auxiliary equation becomes, okay, with this substitution, okay? All right, so that finishes this topic. It gives a way of solving this. So if you ever see a differential equation which comes to this form, this is the way that's the easiest that you can solve, okay? So, all right, thank you. We will take things forward in the next class.